I'm going to start recording, and then why don't we just go ahead and start, and people will continue to come in, and we'll again share this recording. Lori, I'll do a very brief introduction to you, and you fill in any gaps that you feel people should know. But I think the most relevant aspect is that you are the director of NASA's Planetary Science Division. My favorite division of NASA sciences, I think it's okay to say to this audience, near and dear to my heart. And I want to thank you so much for taking time out of your day to join us and brief the members of the Planetary Society who are going out and just putting their hearts and effort out there to support space and space exploration and planetary exploration. So I will turn it over to you, and I will look for a few questions after Lori speaks, and then we'll move on to Lindley Johnson, who I will introduce, well, might as well introduce you now, is the Planetary Defense Coordination Officer, one of the best titles in government, I think. He'll be giving us a status update on NASA's planetary defense activities. And then Kelly, I can't keep track of your rocketing career. What's your title now these days?
I manage the Near Earth Object Observations program for Lindley.
Okay, thanks. I knew it had changed, but I didn't remember off the top of my head. So we have experts on planetary defense and the expert on NASA's planetary program here to share us with information. And I should also say, Laura, we had Sean Mahoney from Maston Space Systems here earlier today, talking about some of their work on the CLIPS program. So we got a nice discussion on the commercial lunar payload services. That was really great. So Lori, over to you. And thank you again for joining us.
You bet. It's my absolute pleasure. Always nice to get a chance to talk with the Planetary Society. Really appreciate getting to have this opportunity. And I'll tell you, Casey, I'm with you. I also am biased. I would say that planetary is the coolest science going on at NASA. Again, I'm a little biased. I did also want to introduce Shoshana Weeder, who's on the line as well with me. She's works within the Planetary Science Division. She's one of our research and analysis program officers. She's also my executive scientist and works closely with me on making sure I have some nice things to say to you when I get to the opportunity. So with that, why don't we move on to the next slide. As Casey said, I'm going to just give you some highlights of our planetary program. Lindley's going to focus on the planetary defense side, so I'm not going to talk about those here, but certainly a really important part of the planetary program. Right here, my favorite slide. This is our current Planetary Science Division fleet. It really is an incredible time to be a planetary scientist. There are, at this moment in time, 32 missions on this slide, 32 missions and growing. And about half of those are in operations. You can see from the fonts over in the bottom left, the ones that are in green or blue font are in operations, and the other half are in development, either in formulation in yellow or in implementation in orange. And this includes the ones that we're leading from NASA and also the ones we're partnering with our international partners on, other agencies. But really just an amazing fleet that spans the solar system and doing an incredible amount of science in a lot of different size categories. So what I'm going to do is just kind of hit a few highlights, things that are hot topics in our world today. I think recent happenings and things that are on the horizon for us. So if you go on to the next slide. Of course, the big thing, of course, was the Perseverance landing on February 18th. You would have had to have been sleeping quite hard and soundly to have missed this one, because it was just an amazing event. The technological achievement was incredible, and the engagement with the world was absolutely phenomenal. Really a fun event to watch, and just fills fills me with an incredible amount of pride to even just be a small part of the NASA family that was able to achieve this incredible landing. Next slide. So I'll talk just a little bit about the Perseverance mission and March 2020. I know all of you know this very well. Of course, we landed in Jezero Crater. You can see the Octavia Butler landing site there where we touched down in close proximity to the river delta there, which is hoped to be a potential place to look for evidence, fossil evidence of past microbial life that may have existed over 3.5 billion years ago, and carried into the crater via the waterways that would have been present on Mars at that time, and then deposited in the river delta as that water flowed into the standing body of water. So we're really looking forward to getting over to that river delta and start to exploring. But on the way, we will be exploring the geology and the geologic history of the rocks in the floor of the Jezero crater. Next slide, please. The primary objectives of this mission, again, as I know you know, are number one, the geology, trying to understand that geologic context, trying to put together the geologic story and history of Mars, the early part of Mars, and in particular Jezero crater. Objective B is the astrobiology goal, as I mentioned, looking for those microfossils that may be present in the river delta or in the other regolith that surrounds the area. And then finally, objective C, ultimately collecting samples of that material, a diverse set of materials, both focused on the geologic history and the astrobiologic history that can be returned to Earth for analysis back in our own laboratories. And then we also have the supplemental objective of helping to prepare for human life. And there's human exploration of Mars, a variety of different experiments on this mission that are helping us prepare. And I'll talk a little bit about those on the next slide, where just showing our incredibly capable scientific payload. I'm not going to talk through all of the amazing instruments that are on this payload, but very specifically designed to help us contextualize the environment and help identify which samples might be best to collect, where we want to drill, and what samples we want to bring back to Earth. And as I said, in addition to that incredibly capable payload, we also have a variety of technologies that are being demonstrated on this mission and that are helping us lean forward and prepare for human exploration. One of those was the Medley 2, which is that sensor suite that was on the entry and descent system on the aeroshell, that highly instrumented aeroshell. We learned from the Medley 1 tech demonstration on Curiosity to help us refine the experiment for Perseverance, and really a highly instrumented entry system there that will help us to better design and more efficiently design entry systems for the much larger systems that are going to be required for human landing. We also successfully demonstrated the terrain relative navigation technology, which allowed autonomous navigation as we were executing the descent and coming down on the descent system, to be able to in real time check the images of the surroundings as we came down with onboard maps, identify small patches of safe areas to land, and then maneuver to those areas. And then we successfully landed on one of those small postage stamp areas that was a safe landing. Incredible technology demonstration there, which will also help for future pinpoint landings. And then ultimately the Mars helicopter technology demonstration, which I'll speak a little bit more to in just a moment. If you can go on to the next slide, please. I love this image. This is one of the early ones. I know a lot of images have been released now, but this was one of the first panoramas that was released, and just that sense of being on the surface of Mars and looking around within Jezero crater. You can see in the distance the crater wall, and then you can also see coming up on the right-hand side there, kind of in the mid-ground, the front of that river delta in the near distance. And so just an incredible sight to see. And then the imaging systems that we have are just amazing. And I think if Shoshana can click on this one, you get a close-up of one of these larger deposits that's out there near the river delta. You can see the crater wall in the background, but just these massive blocks that are out on the floor of the crater that may indicate some potential flooding events that may have happened in the past. Really incredibly looking geology there for us to explore. Next slide, please. We'll talk a little bit about what's been going on over the last month and a bit, about 5 weeks since we landed. Everything is going really well as far as checking out all the capabilities of the rover. Of course, we've now driven quite a bit. We've tested out the robotic arm. We've been testing out the instruments. Everything seems to be going really well on that front. You go on to the next slide. The next big thing is the helicopter, and we've been maneuvering over the last several days, the last several sols to get into the spot the airfield where we're going to deploy the helicopter. The Perseverance rover has been in that location now for a couple of days and has been methodically executing the maneuvers required to deploy the helicopter. You can see the image on the right. Was just taken in the last day or so, where we now have the helicopter is now vertical and all 4 legs have been deployed. As we do this experiment, we are just doing it step by step. We have a plan, but we also want to make sure that each step is executed correctly and that we fully understand what's going on before we go on to the next one. But so far, things are going very well. Next slide, please. And this just shows the location of the helicopter drop-off location. Inside that square, you can also see the lines that are drawn on the map show where we landed. The rover landing site was just outside of the flight zone. And then we traversed through the flight zone where we drove up and dropped off the debris shield that was covering the helicopter. And then we drove back to the flight zone where we're in the process now of depositing the helicopter, and then once it is safely on the surface, the Perseverance will quickly back away so that it can begin charging its batteries with the solar panels, and then drive off to a safe distance where we'll be observing that first flight. And that observation location has been given the name of the Van Ziel Overlook in honor of Jacob Van Ziel from JPL, who was a longtime advocate of the technology developments and particularly the helicopter. So he unfortunately passed away last summer unexpectedly, and I think this is a really nice honor to his legacy. Next slide, please. And of course, Perseverance with those cached samples is, of course, the first leg in Mars sample return. And things are moving quickly and very well with Mars sample return. I'm sure you all are pretty aware of the architecture that's being explored. It's a very strong partnership with the European Space Agency. Will involve the launch of a European Earth return orbiter that's carrying a NASA-developed capture and containment system. That orbiter goes into orbit around Mars, and simultaneously a US launch of the sample return lander carrying a fetch rover, and the Mars Ascent vehicle is launched, will land on Mars. We will send out the fetch rover to collect the samples, and with luck, Perseverance will also be able to return samples back to the sample return lander, load them into the Ascent vehicle, launch them into orbit around Mars for capture by that Earth return orbiter, which will bring them back to Earth. We went through several reviews in the fall, including a review by the Standing Review Board, which has been established for this mission, as well as an independent review board. We also did independent costing and schedule assessment to assure that as we kick off this incredibly ambitious mission, that we have the right approach, we have a good design, we have adequately allocated the costs and schedule for this mission. And so those independent reviews were incredibly useful and helped us to move this mission into phase A, which kicked off late in the fall. And that is moving forward very well. We also have a lot of activities ongoing to further define what the needs will be for the receiving facility once the samples are returned back to Earth. We're working closely within the Mars Exploration Program to assure that there is the fundamental science underlying this mission all the way through, and to assure that we're prepared when the samples are returned back to Earth. And there's a lot of work going on there to help define the requirements for that facility and how we are working closely with our partners in Europe. Next slide, please. So there are a lot of other exciting things going on in Planetary besides just Mars Perseverance and sample return. Last fall, OSIRIS-REx successfully conducted its touch and go sample acquisition on October 20th. This was, again, an amazing technological achievement, being able to maneuver that spacecraft from several hundred million miles away to within 1 meter of the target location and collecting not just a sample, but a robust sample that was filled our sampling head to the extent that you can see in the top right-hand image there. You can see actual particles escaping from the sample head, which caused a little bit of excitement. And so we kind of moved a little faster in our schedule than was planned. We were able to button up that sample return head in the capsule to make sure that we preserved as much of that sample as possible and didn't allow any more to escape. And so now the spacecraft has been hanging out at Bennu, waiting for the right dynamics to return home. And they are just in about a week from now, next week on April 7th, going to do a final flyby of Bennu to do some imaging of the asteroid, particularly focused on imaging the sample site at Nightingale, so we can do some before and after comparisons to better understand how we disturb the surface. And then on May 10th, the spacecraft will begin its journey home, expecting arrival in September of 2023. Next slide, please. And we also have some cool stuff on the horizon coming up. Our next big event is going to be the launch of the Lucy mission in October of this year. Lucy, of course, the mission to visit multiple Trojan asteroids with the Lucy spacecraft. This mission is in its integration and testing phase, everything going extremely well. Even despite all the challenges of COVID over the last year, this mission is on schedule and on cost, going along extremely well. And they are working towards shipment down to the Cape in the middle of the summer with the launch window opening in October. And again, really excited about that. We've also listed on here some of the great engagement activities that are out there related to Lucy, including some activities for students and others in the public community that are interested. Lucy project is doing some really fantastic engagement and outreach activities. Next slide, please. And just following Lucy will be the launch of the Double Asteroid Redirection Test. Of course, this is the first flight project within the Planetary Defense Line. I feel certain that Lindley will talk to this a little bit more, but just to give you a brief update, this mission was previously targeting a launch in the summer, in July, but we recently did an assessment of their schedule, some of the technical and schedule risks, and determined that it would be best if we shifted to the backup launch window, which opens in November. And so there was recently, the project was given direction to shift to that launch window in November. And the project is now moving forward very well towards that target launch. And again, I expect Lindley will say a few more words about DART. Next slide, please. So I heard that you got a briefing earlier today about from Masson about some of the commercial lunar payload services. I just wanted to mention as part of Artemis things, Planetary Science Division and Science Mission Directorate are playing important roles in working with human exploration on the Artemis program. We feel it's important for exploration and science to work hand in hand, and SMD has important contributions that we can make. Then on the bottom left, you can see the early South Pole robotic landings. These are primarily the CLIPS missions that are being worked on. My next slide will show a little bit more about that. But in addition to those CLIPS missions, we're also developing the Viper mission, the Volatiles Investigation Polar Exploration Rover. This project is moving along very well. They just recently were confirmed, and so now are in phase C of their development. And we've also completed the procurement for the CLIPS lander that will deliver the Viper rover to the surface in late 2023. Next slide, please. And just a quick, again, thinking about all the exciting things going on this year, the first 2 CLIPS deliveries are expected by the end of this year. By the Intuitive Machines delivery in November to Oceanus Procellarum. And then the second delivery from Astrobotic to Lacus Mortis happening at the end of the year. So those two are happening in 21. But if you click again, Shoshana, I think we'll see the 22 deliveries that are already on the books that will be happening. We have 2 more in 2022. And if you click again, I think you will see 3 more planned for 2023, including the delivery of Viper to the South Pole. And then you've got the Firefly delivery in 23, and then 1 TBD, and then another one in 2024. So we're working to keep up that cadence of approximately 2 per year of these CLIPS deliveries. And with that, I think I will stop talking. If we go on to the next slide, I think that was the last one. And I can take a few questions, Casey. Again, I can't cover the entire portfolio in 20 minutes, but I hopefully give some highlights and happy to take a few questions.
Thank you. And you know, great problem to have that we can't cover the whole Planetary portfolio in 20 minutes. That's fantastic. We have a couple questions I'll just pluck out here. One about Mars sample return, and this is something I'm interested in too. And I'll actually preface this by saying Mars sample return is just amazing that we're in phase A, that we started this project. I remember looking through NASA's budget history, and the first mention in the presidential budget request about a sample return mission to Mars was 1978. They requested money for it, for a theoretical like 1986 landing. So this has been in the works, you know, for a long time. So kudos for helping to get that through. And so to that end, one of the questions is, what are some of the unexpected challenges that you've already been running into once you've actually started to turn this into a real mission? What are some unexpected discoveries of that complexity that you could talk about?
Oh, that's a big question. And it is a challenging mission. And I don't know that I would say it's unexpected, but it is, as you can imagine, it is complex. And that is in part the beauty of the collaboration that we have with European Space Agency, which is wonderful. It's enabling, and it's a really, really strong partnership, but it's also, you know, brings its own complexities. And then just the development of everything that needs to go into the sample return mission is going to be challenging. And we recognize that, and it's going to be a lot of work. One thing that we've done, I'm sure you've seen, is that we did separate out Mars sample return from the Mars exploration program for management purposes, so that we could have really focused attention on all of those complex relationships that are required to make this successful. And so Thomas Zurbuchen brought on Jeff Gramling as the Mars sample return director back in the summertime. And that, you know, Jeff is solely focused on the success of this mission, the success of delivering the mission to Mars, and the success of bringing those samples back to Earth. And I think that's going to be critical to the success. I think this is a lesson learned from things we've seen with large missions like James Webb Space Telescope, which also is now, you know, managed separately outside of astrophysics. Again, for that, for the purpose of increased focus and visibility, and to ensure the success. And as you said, Casey, you know, this has been a dream for a very, very long time, and we're in a fantastic position right now to finally get to execute this mission. We're closer than we've ever been, and we want to make sure we get it right. And so we're working really hard to make that happen. Yeah,
no, it's just very exciting. And I think looking at the international response to the landing of Perseverance reminds us, like, when, you know, NASA's attempting to do these really bold and exciting, difficult missions, that's when you kind of get the best response from people. People really seem to react to that. Like, you're just really pushing the envelope. Okay, one more quick one, and then we'll move on to planetary defense. So this is, I'll just kind of combine a couple of questions here. Someone's asking about a future, you know, is there going to be any future missions to Venus? And I'll just pair that with, what theoretical mission would be your favorite addition to the current planetary fleet? So I don't know if you can say that one publicly. That's dangerous territory.
I'll have to be diplomatic. So first, let me answer the Venus question. So as I'm sure folks know, there's an incredible amount of interest in Venus missions. There has been for quite some time, of course. but there are actually 3 Venus missions in competition right now, 2 in the US and 1 in Europe, that are vying for potential slots. So within the US, there's 2 Venus missions under consideration within Discovery right now, 2 out of the 4 that are being considered. And then in Europe, within ESA, they're having their M5 competition, and they also have one of the 2 missions is a Venus mission where they're competing against an astrophysics mission because, of course, their portfolio encompasses a much broader scope than ours. But so there's 3 that are out there. 3 of the 5 missions that are competing are Venus. So, who knows? Maybe that means there's a good chance. I suppose some folks out there on Planetary Society know that I have a past history with Venus and a past relationship there. So I have to love all the planets equally, but I do think it would help balance our portfolio to have a Venus mission. So we'll see what happens with the Discovery and the M5 selections. I'm actually recused from those, I will state publicly, because of my past Venus relationships. As far as dream missions for the future, I do think there are several opportunities out there that can help us expand our knowledge in areas that we don't have. I'm always interested in trying to expand the portfolio into areas that have been, for lack of a better word, underserved. And so I have a lot of hopes there, and a lot of those hopes are resting with the decadal survey right now. So that's my diplomatic answer, is that I'm really hopeful that we get some great guidance out of the decadal survey on where we should go next to help fill out the breadth of our portfolio.
Great. Thank you so much, Lori. And so we'll bring on Lindley to discuss planetary defense. And Lori, just to be clear, you'll stick around, it sounds like, for questions at the end?
I will, yes.
Okay,
I'll be
great.
there.
So keep putting in your questions if you think about them for the broad planetary program. We can get to some of those with Lori at the end. And otherwise, I'm very happy that Lindley Johnson is here with us today. He's again, the chief protector. Someone I think called you the Earth's goalie, trying to keep it from being hit by.
I heard that one.
Yeah, so Lindley, I'll turn it over to you if you want to add anything that I didn't quite describe correctly. But otherwise, let us know. Oh, you and Kelly, I should say, too, who's running the near Earth object observation aspect.
Yeah, I twisted Kelly's arm to join me today to give this overall briefing for planetary defense. And I actually get started here a minute or so early. That rarely happens when all of planetary science is being discussed. So I appreciate that, Lori. So the briefing we're giving you today is a broad overview of our total planetary defense program. I know the Planetary Society has a particular interest in the Near Earth Object Surveyor mission, but even though that's going to be a big leap in capability for us, it fits into a much broader program that we have here at NASA for planetary defense. So we're going to give you a sense of all of that and how it fits in. And Kelly, being the program manager for our Near Earth Object Observations program, manages a good deal of that, all the projects that are in there and that portfolio. Next slide, Kelly's going to flip slides for me here because I'm not capable of doing it. No. I think this audience mostly knows what near Earth objects are, but just to be sure, near Earth objects are asteroids and comets whose orbits can bring them within about 30 million miles of Earth's orbit because they enter the inner solar system. In fact, their definition is actually distance from the sun, not distance from Earth. But these are objects mostly have come in from the main belt, but other sources as well that could pose a future hazard of impact to the Earth. So we are looking for this overall population, but particularly focused on finding those that are potentially hazardous to the Earth. And that's a subset of this population whose orbits can bring them within 5 million miles of Earth's orbit, and therefore, indeed, over the course of the evolution of their orbits, could impact the Earth. Also, the size as well. The Earth's atmosphere does a pretty good job of protecting us of all the small stuff that impacts every day on the Earth. And so we need to be particularly concerned about those that could cause significant effects if they were to impact the Earth. And finally, just as an example, the orbit of Bennu, which, as Laurie said, was the destination for our asteroid sample return mission and is about to start its way back. But Bennu will continue to be engagement with the Earth because it has one of the most significant possibilities of impacting the Earth out in the latter years of the next century. Next, Kelly. So the Planetary Defense Coordination Office, which I head up, and Kelly helps us manage a lot of the activities, is now a little over 5 years old, established in January of 2016. But as you see, NASA's involvement in near-Earth objects and finding this population and understanding it goes much further back than that, over 20 years now. But our task is that we're set up to detect any potential of a significant impact of Earth by asteroids and comets, have the capability to appraise what the range of effects could be from that impact. Is the object small enough that Earth's atmosphere will take care of it for us, or is it of significant size that it could survive all the way to the surface and do significant harm? And how much damage could that be? What might be the radius of those effects so that we can prepare our leadership and decision makers on and advise them on what might be the prudent action to take for a particular event. And so that goes along with the last bullet, develop the strategies for mitigating any impact effects that might happen on the human population or our supporting infrastructure. Next slide. So we have here what we call our strategy slide. It presents all of the major elements of the planetary defense program. Starting up at the upper right, a good deal of our efforts, of course, are to search, detect, and track these objects so that we know what their orbits are and whether they will present a hazard to the Earth over the course of time. Then the second biggest sector is a characterization, ability to determine, well, first of all, the size of these objects, because that leads directly to estimating what the effects could be, but also their compositions, their shapes, and the body dynamics, which could be significant factors depending on what technique might be used to mitigate them, be it in space or effects closer to the ground. Also, a good part of what we do are planning and coordination activities, not only within the agency, but across the U.S. government with other U.S. government agencies or interagency work, and internationally, our counterparts in other space agencies across the planet, European Space Agency, Japanese Exploration Agency, and even work within these international bodies like the International Asteroid Warning Network and the Space Mission Planning and Advisory Group with both Roscosmos and the Chinese Space Agency as well. Then a major part of what we're doing now with the DART mission is looking at mitigation technologies and techniques. DART being a demonstration of kinetic impactor, but we're also working a lot with the emergency response community in the event that we don't have time to do a deflection in space and have to take the hit on the ground, so to speak, in preparing them for what they may be facing and activities that could protect human life and property. And finally, we need to, of course, be able to assess our success in all of these areas. How well are we doing? Do we need more capability? Can we successfully predict these future impacts or have the knowledge to do an in-space mitigation mission? Next slide. Our guidance these days comes from a plan that was released by the White House now a couple of years ago. But this strategy and action plan was something that was at least 5 years in the making. It began under the Obama administration with the overall strategy, which was released in 2016. And then the accompanying action plan to address that strategy was in this June 2018 report. And that's available to all to go see at that link. And next slide, what this strategy and action plan is actually breaks down the mission area into 5 areas, goals. And what the plan really is a 10-year, lays out a 10-year plan and strategy for improving our capabilities to address a potential impact threat. So, of course, the first goal is to enhance our capability to find them and know where they're going. You can't do anything about them unless you know they're there and where they're going. There's a lot of modeling and analysis work that goes into determining what the threat is, when it's going to be a threat, how big a threat it's going to be, so that we can advise decision makers about what we might be facing. And then, of course, developing the technologies and techniques for an in-space deflection of an impacting asteroid. Also, a major goal for the plan is increasing the international cooperation and awareness of the NEO threat, bringing resources to bear across the planet. Not only if we had to do a mitigation campaign of several missions to deflect an asteroid, but just simply finding them and characterizing them in the first place is done across the international community. And then within the U.S. government itself, establishing our impact emergency procedures and protocols is the last area of big work. Next slide. So with that, I'll turn it over to Kelly to talk about the NEO observations program.
Right, as Lindley mentioned, really the first order of business for planetary defense is finding the near-Earth objects before you can actually do anything about them. And so it's like finding a needle in the haystack, as I'm sure many in the Planetary Society are also amateur astronomers and take your telescopes out. As you can see here from this image from the Catalina Sky Survey, there's an asteroid going through that starry field, and it just looks like another star. So it is like pulling a needle out of the haystack, but we've got a fantastic program of some really capable projects and fantastic people who are really good at doing just that. But NASA's program actually goes all the way back to 1998. So NASA's been doing this sort of work for a long time. But in 2005, the NASA Authorization Act kind of set the current priority objective. It evolved amending the National Aeronautics and Space Act of 1958 to make NEO detection, tracking, and research one of 7 explicitly stated purposes of NASA. So NASA is supposed to be doing this work. And NASA was also directed to find and catalog 90% of the near-Earth objects greater than 140 meters in size within 15 years by 2020. That size range kind of came out of science definition teams looking at kind of that area of what size do we have, are there regional consequences from an impact? And so this is something that was supposed to be completed by last year, and we're not there yet, but you'll hear about capabilities to try to accelerate toward that congressional goal that has been given to NASA. And that is referred to as the George E. Brown Jr. Near-Earth Object Survey Act. And so NASA's current search program has a number of ground-based telescope assets that are providing most of the discoveries of near-Earth asteroids. The Catalina Sky Survey at the University of Arizona has 2 telescopes participating in the effort, and also the University of Hawaii has their 2 Pan-STARRS telescopes on Haleakala, and these 2 telescopes are providing the bulk of the new discoveries. But also funded by the program are the Atlas telescopes, also at University of Hawaii, which are smaller telescopes surveying the sky, maybe not as faint, but quicker in order to maybe catch what might fall through the cracks. And it's producing a lot of interesting discoveries and comets. And those telescopes are in Hawaii, but 2 more sites are being commissioned in Chile and South Africa, hopefully later this year, despite delays due to COVID. That's still been rolling along. Also, we do, NASA does coordinate with the US Space Force on the Space Surveillance Telescope that the Space Force and Australia are operating. This used to be in New Mexico, and the Linear project at MIT Lincoln Labs worked to retrieve asteroid non-natural detections, or rather natural detections from the images that were searching for non-natural detections. And that project is going to continue to do that now that that telescope has been moved down to Australia. And so that will also, along with Atlas, provide good Southern Hemisphere coverage. And we also partner with Caltech's Zwicky Transient Facility. We're funding retrieval of asteroid detections from its survey. And then finally, there's NEOWISE, which is the repurposed WISE mission, the Wide Infrared Survey Explorer, which was an astrophysics mission. And it also discovered asteroids, because asteroids like to photobomb any kind of sky survey. And so after its cryogenic channels ceased to function when it ran out of cryogen, it was later kind of pulled out of hibernation by this program to continue its survey and with the non-cryogenic channels, and to continue to detect near-Earth asteroids and other small bodies. And so it's making discoveries, but it's probably a more significant contribution is in the area of characterization. Looking in the infrared, it can retrieve size information that is more accurate than what you can get from the optical measurements from the other telescopes. So very capable set of projects here. This program also funds the Minor Planet Center, which is the International Astronomical Union recognized repository for small body position measurements from around the world. And we do fund that, and it's managed under the Planetary Data Systems Small Bodies node. And observations from observatories around the world, whether NASA funded or not, on near-Earth object positions or any small body positions are fed into the Minor Planet Center. And they do the identification. Is it a natural object? Is it something we've seen before? Is it a new discovery? Designation, initial orbit computation. But then also part of this program is the Center for Near-Earth Object Studies at JPL. And they take those observations or those position measurements, and they do the precision orbit analysis. In the short term, they'll take observations or positions that it hasn't even been confirmed yet if it's an asteroid or if it's real, but to just look right away, could this pose an impact threat in the short term? But also taking the orbits of confirmed objects and tracking them out into the future, into the next century, to see, are there any long-term impact threats that we need to be aware of? And in the event of that situation, they would calculate the time, the location, and the geometry should we ever find ourselves in that situation. Now, also, as Lindley mentioned, working with the international community, NASA does participate in these larger efforts that have been recommended by the UN Committee on the Peaceful Uses of Outer Space. We work with their Office of Outer Space Affairs. And these 2 bodies were set up in order to coordinate the worldwide effort or increase the communication. One of those is the International Asteroid Warning Network. And we actually had a semi-annual meeting that wrapped up just a few hours ago. So we're fresh out off of that. And that's a worldwide collaboration of mainly observers, mainly the astronomers, space agencies, universities, observatories, even some very capable amateur astronomers. I hate even using that term because they are very professional, and also orbit analysts and modelers are signatories to this International Asteroid Warning Network, or IWAN, as we say, and to try to coordinate better on the effort to find and characterize the NEO population. And that body, or collaboration rather, the signatories of that collaboration would notify in the case of a detected threat. And then also there is the Space Missions Planning Advisory Group, which is a collaboration of space-capable nations looking at potential deflection mission plans in the event that there is an identified impact threat in the future. And so space agencies and offices of space-capable nations are collaborating in that area. And getting back to the International Asteroid Warning Network, we have a lot of signatories. I need to now make a new slide because I can't fit everybody on here anymore, but we have 30 signatories to the International Asteroid Warning Network. And you see NASA and ESA on here, and then all of the efforts that they fund fall under here too. So it's even larger than what you see here. So it's becoming quite a capable network of essentially everybody doing what they're already doing as part of their own missions, but saying that we're putting our assets toward doing this work of planetary defense and of trying to detect a potential threat. And as this body continues to meet, or this collaboration, trying to improve communication and coordination in order to be more efficient through this collaboration. And the IWAN meets twice a year, and it reports annually at the UN COPIS Scientific and Technical Subcommittee meeting. This was a larger forum a few years back, and this would normally happen in Vienna, and it's been rescheduled actually to a few weeks from now. Normally would be in February, and so this will be happening remotely. We'll be reporting out again, but both IWAN and Same Page report out to this committee of the UN. And so where are we right now with doing all of this? As I said, NASA search started in 1998. And so you can see on this plot with time, the number of discoveries goes up. There's different size regions here. And we had a kind of milestone just recently where we broke the 25,000 number for near-Earth asteroids of all sizes. And so that kind of is represented in the blue plot. The yellow region represents that George E. Brown NEO survey goal that Congress gave to NASA of finding the 140 meter and larger near-Earth asteroids, the one that could pose much more of a hazard. And at least you see down there in red with the 1 kilometer and larger, you see that's really leveled off. The nice thing is there's a real good handle on that population. Maybe only a couple are found every year now. It's these other populations, 140 and larger, and then the smaller ones that are continuing to go up. And so we press ahead. That population, the George E. Brown population there, as you can see, the greater than 140 meters, it's getting close to 10,000. And it's expected that we'll probably break that, hopefully, by the end of the calendar year. The PHAs are noted there. And there's also 113 near-Earth comets that fall into this definition. And so looking at this over time with the different surveys, you can see how all of these colors represent different surveys like the ones I just mentioned, funded by NASA in recent years, that have contributed along the way. Catalina in green, Pan-STARRS in pink, and then the others in recent years. How the capabilities have continued to grow and the discoveries have grown. This is pretty impressive because in 2020, despite some observatory closures temporarily due to COVID, due to fires in Arizona, it's really amazing actually to have hit a new record like this. So there were almost 3,000 near-Earth asteroids discovered in 2020, and that's a record. So of all sizes, 710 so far in 2021. But then we look to the that 140 meter and larger population. It still did quite well, actually impressive that we broke last year under COVID. So there were 551 discovered, but you can see that things have kind of leveled off in recent years. It's getting harder to really push through to improve the capabilities for what we, in the systems that we have right now, to accelerate that number of these asteroids to go kind of further and fainter and pick these up further away from Earth. And so kind of hit the limits of this capability, but at least it's still performing well, even despite COVID. And I'm going to pass it back over to Lindley.
Okay, well, that population of 140 meters and larger, according to a number of studies that have been done on how many could be out there, and what do we need to do to achieve this George E. Brown survey goal. 25,000 is thought to be the overall population. So this pie shape, pie chart, and sectored in the various size regimes. We've pretty much found the 1 kilometer and larger, maybe 40 or more out there according to the population, and down to about 300 meters in size, which in total with the 1 kilometer is about 25%. So the vast majority of them are smaller than 300 meters in size that still need to be found. Overall, we've found just shy of 40% of the population. So we still have just over 60% to go. And if we try to do this with just the current capabilities that we have, finding about 500 a year, it's going to take us, about 3 more decades to achieve the goal. So we obviously need to improve our capabilities to be able to do this in a shorter time period, so we really understand if there is any significant impact hazard out there. And so that's where the NEO surveillance mission comes in, and the space segment of that being the NEO surveyor. That is specifically designed to detect this population using infrared capability, where the objects stand out more against the background of stars, and would be able to find at least 2/3 of the population within a 5-year operational mission, and achieve the overall completion of this survey goal within 10 years of operations. Another advantage is we can estimate sizes directly from those observations with the spacecraft, and have a much quicker understanding of the size of objects we might be dealing with. Just like all the other projects, though, it would deliver the astrometric tracklet data to the Minor Planet Center to fold into the continued worldwide effort here. And so we've been pursuing this project for several years now, as many of you know, and we're just about to get it into the phase B of its development. The key decision point B for NEO Surveyor is now scheduled for the end of May. If you can click that last one there, Kelly. So it looks like we are really getting over the hump on this one, and getting it into development here soon. Next slide. So this shows why it's really advantageous to us to operate in the infrared. 2 asteroids of the same size, one very light and one very dark. In the optical spectrum there on the left, the light-colored one is easily detectable, but the dark-colored one is not in the optical. But if you look in the infrared, because the signature there is based upon closer to the size of the object, they can appear about the same sized signature, and therefore are more easily detected in the infrared. Next slide. So positioning of NEO-Surveyor, this first part of the graphic shows you the field of regard that NEOWISE has, which is in a low Earth orbit, a sun-synchronous orbit, and looking with just a little under a 1 square degree field of view, perpendicular to the Earth's sun line. So a very limited coverage that takes it 6 months to be able to cover the whole sky, as opposed to the NEO-Surveyor mission, specifically designed. We're going to position it at the Earth-Sun L1 point, looking out at the sky, both wide swath in front of the Earth's orbit and behind the Earth in its orbit, switching back and forth every about 2 weeks, and we'll cover a much larger portion of that near-Earth object population much quicker. Next slide. And I'll turn it back to you, Kelly, for this case study of a very interesting object that was found a couple of years ago. And you're muted.
All right, it's hard to drive and mute at the same time. All right, yeah, this was a lot of fun in a way because it was a chance to test the system in a non-threatening way. In 2018, there was a small asteroid discovered by the Catalina Sky Survey, and it was less than 3 meters in size from size estimates. So nothing that even warranted warning about or anything, but a good chance to kind of do a little exercise with it, because it turns out it was discovered 8 hours prior to impact, and it was only the third object that has ever happened where it's been discovered prior to impact, third asteroid. And so on top of the discovery images by Catalina Sky Survey, there were some additional observations retrieved from the Atlas telescopes in Hawaii, and you can see the orbit here on the plot of this very small asteroid. So nothing worth warning about, but a good chance to do an exercise. So the Minor Planet Center and the CNEO's JPL warned Planetary Defense Coordination Office of a potential impact. And so CNEOs does what it does, and it calculated the impact corridors with the available data. And now that when it was first discovered, this was the impact corridor that was calculated, which covered from the Atlantic, across Africa, Indian Ocean, out into the Pacific. But then once the Atlas observations were folded in, and what tends to happen in general, if you can get more data, you can really narrow things down. And so in this case, it narrowed down the impact location to the southern part of Africa. And that's all that had before impact, since it was only 8 hours. But then sure enough, at the time predicted by CNEOs, there was a bolide, a fireball, detected over Botswana at the right time. In addition, there was a security camera that was going, and sure enough, there is that object, the asteroid, entering the atmosphere. Now, it didn't actually impact the ground. It's over the horizon from this point of view. So it disrupted in the atmosphere, again, something that size 3 meters. Our atmosphere does a good job with that, and it just creates something very pretty to look at. And it was nice that it was captured in this way. But it was also captured by US government sensors, which we coordinate with the Space Force on retrieving natural objects that enter the atmosphere to use for scientific purposes. And they're on the website there at JPL CNEOs. And it detected this bolide from 2018 LA. And so it was detected in that way. And then also Comprehensive Testband Treaty Organization infrasound sensors also detected the bolide. So it was a nice experiment on many fronts. But then finally, meteorites were recovered from this entry of this asteroid. So there was a meteorite fall. And from a scientific point of view, it's really interesting to be able to observe an asteroid out in space and then actually get pieces from it on the ground. So it's sort of another type of sample return, and a good way to try to connect all these pieces together as we try to be able to predict what the impact effects might be, what the composition of objects are. So the whole thing was a really nice test of the system in that way. from detection to orbit calculation to warning and to detecting the entry and then following up. And I think this is back over to Lindley.
Yeah. So with the U.S. government sensors, getting the data from those for bolides, fireballs that are detected worldwide, and now our database collected over the last almost 30 years now is quite extensive. There's over 900 events now in this database of events where the size of the object, based on the energy release, is estimated to be larger than a meter in size. So these are all meet the technical definition of an asteroid impacting the Earth, even though most of them are much smaller than would do any significant effects on the ground. But of course, there are a couple of them in here. The first being a Chelyabinsk event back in 2013. That's the, if you click it, I think it will point out that the large event there in Russia in February of 2013. There was another significant event over the Bering Strait here just a few years ago too. That is the high on the list of sized events, not nearly as big as Chelyabinsk though. Next slide. But we collect this data to get a better understanding of the effects that could happen from an impact, and so this goes in kind of the data goes into our modeling of what could happen if we had an impact. And we have a project out at Ames called the Asteroid Threat Assessment Project that studies the physical dynamics of the entry into the atmosphere. If you just keep clicking here, Kelly, it goes through the steps here. First of all, the characterization data that we collect in space, starts out this modeling effort as to what is the asteroid that is coming into the atmosphere. Then the entry physics and modeling the effects of the atmosphere on asteroids of particular compositions. How well does it break it up? Where at what altitude might it detonate, or if not detonate, and be strong enough to reach the Earth's surface? And so what are those effects going to be at the Earth's surface, both blast effect and thermal effects to population centers or infrastructure from an impact? And then finally, the data and information on what is the potential damage and risk to human life and infrastructure that could result from a particular asteroid case that goes into our assessment that we can provide to leadership both in the US and worldwide. Next slide. So we use this information to help feed our work with the emergency response community, and several exercises that we've had with FEMA here in the US. This particular one now a few years ago though, but we simulated the impact of about 100-meter size object. It could impact over Southern California, and knowing about this impact several months in advance to prepare emergency response and state governments for what the effects could be from such an impact, so that they now have some knowledge of what they could be facing for this significant natural disaster. This is one of the only natural disasters that I know of that you can predict well in advance if you're out there looking for it. And we can do this work to determine when and where this natural disaster is going to happen. In fact, with the orbit calculations that we are able to do, we can predict the day several years, even decades in advance as to when the disaster could occur. And so that's sort of unique for the emergency response community to be able to know that far in advance that there could be a natural disaster if we're not able to do anything about it. So in this particular scenario, next slide, we had the impact occur right in the Rose Bowl in Pasadena, California. But based upon the parameters on the size and composition of this object, here's the kind of area of devastation that could occur from an asteroid of just 100 meters in size, devastating over 25 radius of over 20 miles around the Rose Bowl, and some 2,500 square miles of devastation that could occur. So it's something we do not want to happen, and that's why we have the Planetary Defense Program to try to find these things well in advance so we can do something about them in space. Next slide. So back to you. Talk about how do we find out more about the objects once we found them.
Right, after you find the needle in the haystack, you want to zero in on the needle and see if you can retrieve any characteristics so that in the event something does pose an impact threat, you would need to know some of that to do some of that modeling that Lindley mentioned, to know something about the physical properties. And then if it's not going to impact, you've got some fantastic science to work with. So the primary characterization asset for NEOs is NASA's Infrared Telescope Facility, which is funded by this program now, but actually is continuing its mission of support for missions of all planetary types, looking at all planetary targets and astrophysics. But for NEOs, it provides spectroscopy that can yield clues about an asteroid's composition. This is on Mauna Kea in Hawaii. And then also there are the planetary radars, Goldstone planetary radar on the Deep Space Network 70-meter dish that was returned to full power operations late last year after being down for a while for maintenance, developing these klystrons, these kind of light bulbs, these amplifiers that produce the high-powered radar. And so that's operating again. And unfortunately, as I'm sure this group is aware of, the Arecibo had its situation where there was a break in a cable, and NASA funded the planetary radar there at National Science Foundation's Arecibo facility. There was a break in the cable, and they had announced the decommissioning of the site, and after 2 cable breaks, but then unfortunately the secondary collapsed into the dish in December. And so now we do not have that capability, although it wasn't steerable in the sense that Goldstone is steerable, it had greater sensitivity. And so it does at least now has spurred on looking at possibilities for what would be the next step with planetary radar and with newer technologies in order to get that kind of capability and more again one day. Radars aren't used to find asteroids. You can't sweep them like you do with the radar at the airport, but once you know exactly where an object is, you can point the radar at it and you can get some really fantastic information out of it. You can get really precise orbit information because you know the position very precisely. And then also if the asteroids actually pass close enough where you can do imaging, then you can get some fantastic radar imaging and turn that into shape models. And you see binaries, you see triple asteroids, asteroids with satellites, contact binaries. So really very interesting population just from the radar studies. And that's been super useful for planning missions to these objects. I think all asteroids that have had missions have had at least radar ahead of time where possible. And so that's an important capability. Another happening you probably saw in the news that there was an object discovered last year designated 2020 SO by the Minor Planet Center, but as Paul Chodas and folks at the Center for Near Earth Object Studies looked at this and the way the orbit behaved, they realized that this was probably an artificial object and in fact tracking it back and connecting it to the 1966 Surveyor 2 launch, and this was the Centaur upper stage. that had been in orbit around the sun, and it was coming back home. And actually, this was another good exercise. Spectroscopy from the IRTF was used to confirm the artificial nature of this object. So between the orbit and the spectroscopy, learned a lot about it, and it actually came back into Earth's orbit for a couple swings and now is back in orbit around the sun, but another interesting exercise. And then finally, mentioned the International Asteroid Warning Network earlier. They also, as a collaboration, been doing observing campaigns to exercise the system, observing different objects and coordinating different aspects of the positions or the composition of objects' properties. And in this case, looking at the asteroid Apophis, because this is the last chance to get observations of it before 2029, where it's going to make that really close approach of Earth within 40,000 kilometers, within the distance of the geosynchronous satellites. And so asteroids do pass that close, but one of this size, 340 meters in size, that's an historic close approach. And it's actually will be visible with the naked eye from Europe when that happens in 2029. And so the IWAN, NASA was part of that and helped to lead it, coordinated to get observations. And as part of the campaign and as part of the operations within NASA and NISA, the orbit was able to be refined to the point where Apophis has been taken off the risk list. And you probably saw a release on that. That now Apophis is not being carried as an impact threat for the next century, and so that's really great. Maybe disappoints some people who this was their favorite threatening asteroid, but now Apophis is off the risk list, and so it's going to be a fantastic science opportunity in 2029. And the data from this apparition are being rolled up and will end up in the peer-reviewed literature, and also lessons learned for this as a planetary defense type of exercise and how those operations went. And then back to Lindley.
In the last few minutes here, I want to talk to you about impact mitigation techniques and technologies, and the DART mission, which next slide, kinetic impactor technique. The reason we're pursuing a demonstration of this technique first is because it was evaluated by the National Research Council as being one of the most mature technologies that could be used to deflect at least a small size asteroid in space, given several years of warning to be able to get the mission out to it. So that is why we chose it as our first mission to demonstrate capability to deflect an asteroid in its orbit. Next slide. So the double asteroid redirection test, the target that has been chosen is the Didymos system, comprised of the primary asteroid is about a half-mile across, and then its moon, now called Dimorphos, is about the canonical 140, 150 meters in size. I think 160 is our latest estimate of its size. And we're going to impact the moon and change its orbit about the primary, thereby not changing the orbit of this system about the sun. So Didymos is a potentially hazardous asteroid, so we don't want to put the Earth at any further risk from this asteroid, but demonstrating this on the moon of this asteroid that passes close to the Earth during this encounter, so that we can observe the effects of changing the orbit of the moon from the ground, from ground observations. So as Lori said, the launch of DART is now on the schedule for the latter part of November. We actually have a long launch window. It actually goes for several months. We'll be launching out of Vandenberg Air Force Base in California. And then the impact of the moon will occur in late September of 2022. The original set up to, even though we're launching several months late, we still encounter the asteroid at the same time, so that we're still able to observe from Earth observatories of the change in the orbital period of the moon. So next slide. DART is progressing well through its integration and test. The image on the left is of the rollout solar arrays. This is actually technology that we are, new technology that we're continuing to demonstrate for future capabilities. It had undergone some preliminary testing on International Space Station, but this is the first time it is the primary source of power for the spacecraft. The delivery of those two solar arrays was delayed a few months because of pandemic issues with the subcontractor deployable space systems out in California. But those solar arrays are now, I think they're actually at Applied Physics Lab now, our prime contractor for the DART mission. They were to be delivered this week. And on the right is the spacecraft, actually a little over a month ago, as it was going into thermal vac testing at APL and about to be raised into the chamber. It is now, it had a very successful TVAC testing program, almost no issues identified. It's now out of thermal vac, ready to start integration of the solar arrays and then of the Draco camera. The one instrument on the spacecraft used for both imaging of the asteroid and the asteroid system, but also for the optical navigation to guide the spacecraft into Dimorphos. We had some issues with the primary mirror on that instrument, and that was the other thing that caused the delay in the launch. And that camera is undergoing some modifications and will be available to be integrated in the May-June timeframe. So with that, that kind of covers the waterfront for planetary defense at NASA, and we're taking any questions.
Thank you. There would be raucous applause if everyone had their, we're here in person for you. I appreciate that. Great overview of just the amazing amount of work that you're doing. And Lindley, if I remember correctly, I think you told me that you started half-time. You were only half-time as planetary defense, or it wasn't even called that back in the day, right? You were the only civil servant at NASA working on this.
When I started at NASA in 2003, after I retired from the Air Force, actually all that existed then was a part of the planetary astronomy program was dedicated to detection, tracking of near-Earth asteroids. That became the Near Earth Object Observations Program. Back in 2003, it was about $3 or $4 million. We separated out from planetary astronomy as a RNA program on its own to dedicate, $4 to $5 million a year. From that, we've grown it to a full planetary defense program.
Yeah, well, that's amazing to see that growth, and I hope we can keep pushing that forward. So we have a ton of questions, so let me get right to them. We'll start with some planetary defense related ones, and then we'll move on to some more broad planetary ones. So the one that I liked first, let's start with this, because this is a good conceptual one about the type of work you do. They're asking, what's the basis for the study or the claim that there are 25,000 total asteroids larger than 140 meters? How do we know what we don't know if we can't find them?
Well, it's just a statistical study. You examine what you have seen over the course of time, and it's been seen, and also look at your reobservation rate. In other words, for a random sample of observations, how often are you seeing the same thing versus new detections? It's like the marbles in the jar problem. You take out a sample of the marbles, you mark those, throw them all back in the jar, and then you take another random sample and see how many of those that you marked you get back. So it's statistical modeling that's done over all kinds of different things. It's very similar to taking polls for elections, if you believe them.
Work in progress. But okay, so you use basically you can statistically model, and then you can kind of check and validate if your model is correct based on where you're looking and what you're finding.
Yeah, and we go back every few years and redo the update. The last couple of times has been pretty stable, though, at about this 24 to 25,000 number.
So say one was coming. So what someone asked here, what would we do if we find a NEO the size of, let's say, a football field? So it's about 100 meters or so. Do we have capability now to break up or move that object, or would what you're developing for DART, would that apply in that situation?
That's what DART is all about. I mean, we think we understand, we believe we have the technology, we think we understand how it all works, but DART will be an actual real world demonstration of that.
Good. That seems like a good one. And I guess kind of related to that too, I'm seeing a number of questions here kind of about how is Congress and even folks in the Defense Department, how do they consider this problem? And how has that changed over time? Do you think that they're taking it seriously? Or is there kind of do you have to convince people that this is something worth investing in now before it's an obvious problem?
Well, I think now, over the course of 2 or 3 decades of work, we have enough information and understanding of the problem that's out there that even if somebody that knew nothing about the subject were to, spend just a short amount of time to look at what we've collected over the years, would get an understanding that it is a serious concern. It's an extremely rare event, and of course, of a human lifetime, of course, but not all that unlikely that it would occur in a period of a century or so. And in fact, Chelyabinsk, I think, convinced a lot of people that, this is a real problem. Within the science committee, science committees on the Hill, we have gotten good support over the years. In fact, it was the George E. Brown survey that really kicked NASA into the business of looking for these things. Now, the Department of Defense, we share a lot of technologies and techniques with space domain awareness here, and they are happy to support where they can NASA's program for this, but they clearly see it as NASA's in NASA's mission area, not their own. And that's simply backed up by Congress as well. Congress specifically said this is NASA's job.
Yeah, to find them at least, right? I guess who knows if there was a particular issue. I suppose there'd be some. Yeah,
that's not to say that. That's not to say that if we actually found an impactor, it would depend on the scenario exactly how it got handled, whether NASA would be the lead agency or Department of Defense or FEMA. And certainly in a case where we had to take the hit on the ground, that's not NASA's job. That's federal emergencies.
What types of missions are you? Yeah. What types of missions are you looking at? Again, to combine a couple questions, kind of post NEO Surveyor. So assuming that eventually moves forward and launches, how are you setting these long range planning? What types of missions are feasible? Is there anything associated with Apophis that makes sense? What are you looking at or studying at this point?
Well, again, I'll be diplomatic and say I'm looking forward to what the decadal survey comes out with. For this decadal survey, we specifically made planetary defense a part of what they would be looking at to get a good high fidelity look from the community on what should we be doing in the future. Now, of course, the opportunity that PAFAS provides us in the latter part of this decade is pretty hard to resist to do something along those lines. But I'm looking forward to seeing what the decadal tells us.
Right. Yeah, and that was a big change for the decadal to include a planetary defense aspect, and that was a number of at least one report from the National Academies recommending that NASA kind of carve out a specific exemption for planetary defense beyond science, right? To have its own value, because otherwise just competing it on science, it was tough sometimes to choose a planetary defense mission versus,
Right.
Like a pure science mission.
It was clear that it needed to have its own budget to work with, so we weren't, competing, these two, very significant areas of planetary science against each other. But it still is, and I think rightfully so, a part of the overall planetary science portfolio at NASA, because the work that we do is so closely intertwined with the small bodies planetary science community.
Yeah. You briefly kind of addressed this a bit, but maybe worth spending a little more time on. There's questions about how has synthetic tracking and other computational kind of advances in ground-based imaging, has that changed the need for a space-based solution to look for near-Earth objects, or how have advances on the ground improved that kind of detective capability?
Well, we always want to try to demonstrate things on the ground where it makes sense first before we go to the expense of a space-based system, or even decide that we need to go to the expense of the space-based system. What is now called synthetic tracking is a technique that's actually been used by the asteroid detection tracking community for a long time. In its current form, though, where they're pushing the technology now is combining imagery taken by multiple apertures, and so I think that has promise in the future. It needs to undergo some more demonstration from the ground, and it's only in the optical right now, so you don't yet get the advantage that we do from the IR signature, which we talked about, is being able to do fairly rapid characterization of an object at the same time that you're tracking it.
Lori, if you're still there, we've got a few questions. I'll open back up to all of Planetary.
I am
That's
still
just things
here.
that will hit us.
Yeah.
Great. I had a follow-on question that maybe kind of touches on both of your areas, which is how can I'll summarize this kind of, how can planetary defense integrate more with other planetary exploration initiatives? So someone was saying, could it work with Artemis on the moon, or is there things at Mars that could help, being in place, or ride-alongs with other missions, whether small sats or CubeSats, that planetary defense can just kind of work with this broader effort beyond just sending, a mission to this L Lagrange point?
It's an interesting question, and Lindley may, will probably want to chime in, and we may not be 100% in sync on this, but I think, the idea of bringing planetary defense, as an important part of a planetary program, the planetary portfolio, and including planetary defense as part of the decadal survey, is exactly for that reason, right? To make sure that we have the relative priorities for planetary defense and the overall planetary portfolio, which could give us those opportunities. We certainly recognize that there's a lot of great science that can be done with a planetary defense mission. And then we've already shown with some of the science missions that we're making great contributions towards planetary defense with OSIRIS-REx, for example. So I do think there are opportunities there, to leverage, a variety of the missions that we're working on. At the moment, I don't know of any specific examples along the lines of those that are being discussed there. But, that's, again, from my perspective, the benefit of having planetary defense as part of the planetary portfolio. Lindley, did you want to expound?
Again, Yeah. Again, I think that's one reason why planetary defense should be a part of the planetary science portfolio, so we can always be looking for those opportunities, because there are those out there. There are also opportunities, with other NASA programs. We had an effort going for a while called the Asteroid Redirection Mission with human exploration and the establishment of a station around the moon that might have been built around an asteroid had that mission continued. But I think those opportunities are still out there. We certainly want to look for an opportunity in the future, along with some planetary science small bodies mission, to demonstrate a gravity attractor. That's really the next deflection technology technique on our list that we'd like to be able to demonstrate. So we want to look for that. But I also think you need to be careful about not force fitting it, into a mission somewhere and trying to, make something happen just to make it happen, as opposed to something that may not really make sense and end up compromising both sides.
Right. Don't do two things halfway, to say the nice way.
Yeah, right, exactly.
Thank you. So let's see. I have Lori here. Since Mars program right now is kind of focused on Mars sample return, it's kind of big mission. Are there any plans to recreate a competitively selected Mars mission line, and I'll just expand this to say any kind of commercial activities, maybe like Eclipse at Mars type of opportunities to help get more smaller missions beyond just focusing on sample return?
Yeah, I think that's a great question. Certainly that whole landscape we're looking at right now of what else can we do in this time frame, in addition to Mars sample return, as you said, which is it's an enormous endeavor. Going to take a lot of focus. And I did already mention, of course, the science efforts that are underlying in the preparation for the sample return aspect itself, making sure that we're ready to do the analysis of the samples. But as far as continuing, additional remote sensing missions, we're looking at a variety of different things. There is already, we've been talking about a potential of this Mars Ice Mapper, which is an international collaboration to send a radar orbiter to Mars to look for and understand the distribution of subsurface ice at Mars, which is of great interest, scientific interest in understanding climatology and the climate history of Mars, as well as, again, applications towards future human exploration potentially for ISR use. So that is something that we are studying and looking at, and we are also looking at and thinking about, as you said, are there commercial partnerships, some things along the lines of Eclipse. I think there's a variety of things out there. So, we're looking and thinking about those things. There's certainly no lack of great science to be done at Mars, and certainly, the remote sensing work. There's a lot that can be done with remote sensing platforms in orbit. So, yeah, we're looking at a variety of different things. Just nothing concrete yet that I can point to.
Decadal survey. You have to wait for the decadal survey.
Again, I'll defer to the decadal survey.
And there is a new proposed Mars strategy from the Mars Working Group. Yeah, Lindley.
Well, I was just going to say, I see a question here that I'd really like to take about what contribution can amateur astronomers make. Amateur astronomers are already making.
No, I don't have to go, but I did just want to mention, you said there real quickly at the end, Casey, that there is the Mars Architecture Strategy Working Group, did produce a fantastic document, and I did want to mention that. So we do have that work in hand that has a lot of great recommendations for various science program over the next decade.
Great. Sorry to interrupt.
So, I'm sorry, Lindley, go ahead.
No, not at all. That was a great ad there. No, the question about what can amateur astronomers contribute? Amateur astronomers are already contributed for many years to what has become planetary defense. Not so much in the detection side of things anymore, because we're down to a part of the population that are quite small and therefore very dim and require some pretty sophisticated survey systems to be able to detect in the first place. But once they are detected and we have some idea what the orbit is, then those with capabilities that some of the amateur astronomers have can then provide a lot of the follow-up observations that are needed in order to what we call secure the orbit, really get a good enough observations on the object so that we can better determine this orbit, reduce the uncertainties, and be able to project those orbits further and further into the future. And of course, the Planetary Society has had a grants program for a long time themselves, awarding funding to amateur astronomers to be able to upgrade their equipment in order to support the overall international asteroid warning network, not just NASA's mission, but the overall international network.
Thanks for plugging that. Yeah, the Shoemaker Neo Grants program, which one of our grant awardees just last year found a kilometer-sized near-Earth asteroid in the southern hemisphere. So they can. It's an area I think where amateur astronomers can really make real substantive contributions in this area. You don't need like a space telescope necessarily to really help out with this effort.
Yeah, to make contributions. Yeah. And as I said in the beginning, Neo Surveyor is a big step in capability, but it is just a part of the overall puzzle for everything we do. Planetary defense is a team sport. It takes contribution from capabilities across the spectrum of things.
Absolutely. So I want to respect your time. We're a little over. I want to thank you both again. Just real quick, Lori, a question that I've never seen asked of you before that I want to make sure it gets asked. As an acclaimed scientist married to an acclaimed musician, are your girls or scientists or artists or both? I'd love to see or hear you talk about the harmony between science and art.
Oh, there's a lot of harmony between science and art. In fact, I think of science a lot as more of an art than an engineering activity a lot of times, right? The science aspect. So thank you for asking. Yes, I think it's very harmonious. I've actually been with my husband now since 1981. So quite a long-lived partnership there, very successful, going very well. Yes, we have 2 daughters, and the one was pursuing anthropology, but now she is so a bit of in the science area, and now she's teaching science and technology to young people. And my other daughter has gone the more artistic route as a hairstylist, where she gets to practice her art on other people. So a little bit of both everywhere.
Thank you.
Both very talented.
And I learned something. Yeah, and it's a good example. I think that's a nice way of putting it. That science is, you're not just following a set of instructions, right? Like real. And I'm married to a professional scientist, and it's real. Inspiration plays such a key part to that, and
absolutely
giving your mind space to wonder and think and make these interesting connections. It's definitely that integrated aspect of being a human is really expressed in being a scientist.
Inspiration and passion, yes.
And this music, isn't music in a way a science too?
It is, I agree. Absolutely.
That's
a lot of crossover.
Absolutely. All right,
well, I want to
thank Lori Glaze, Director of Planetary Science Division at NASA. Thank you so much for spending your time with us today. Lindley Johnson, Planetary Defense Coordination Officer. Really appreciate you also taking time to join with us today, and extend my thank you to Kelly, who had to leave early, and Shoshana also for helping out today. I appreciate you coming, and all of our members really enjoyed this. I can see by the questions, it's a ton of great engagement. We'll record this and share it with the rest of them who are eagerly looking forward to watching this. So have a wonderful day, and hopefully be in touch with you all soon.
Sounds great. Thank you, Casey.
Bye.
Thanks very much for the invitation.